Got an early bird here. Get you started. Warm your brains up. See if you can do that problem. Or at least make the two-way table for it. It's 500 undecided voters from either New York or Virginia watched the presidential debate. 40% of the voters were from New York. 20% were female. 70% of the undecided voters were male. If we know the voter is from Virginia, what's the probability that they are male? I know my two-way table needs two variables. And so one variable is where they're from. So Virginia or New York. So I'm going to do that first. Virginia or New York. Maybe I should move it down a little bit. Just so we don't mess with my haiku. Born without knowledge. Yes, you are. You're born without knowledge. Yearning to learn evermore. A lifelong pursuit. Forever and forever. We're always learning. Virginia and New York. I'm going to put them up here. And New York. And then, of course, I have to have the total. And then the other one is male and female. I like it. And total. And then we're just going to fill in. Remember, when you're doing these two-way tables, you're going to start with your total. So total is 500. And then I know that 40% are from New York. So you told me that 200 of them are from New York. So, you know, I'm doing 40% of 500. That's all you have to write down. Just show me that much. And then say that 40% of 500 is 200. Our New York is 200. So that means that 300 are from Virginia. Then 20% of the New Yorkers are female. By the way, how did I get that 300? I said 500 minus 200 equals 300. Yes, you can do that subtraction, but write it down and show me what you're doing. Explain to me how you're getting there. So I know of the New Yorkers, 20% are female. So I'm going to do 20% of the New Yorkers. And yes, y'all are getting good at it. You're like, okay, 10% is just 20. I'm going to double it. That makes it 40. Y'all are getting good at it. I want you to be good at that. But you can write it down to show me that you know how to get there. Explain it. And upper level mathematics, that's all we do is explanations of what we're doing. It becomes English almost. So what are those 40? Those are females that are New York. So then the rest of them, so I'm doing 200 minus 40 to get that 160. That are male. And then 70% of the undecided voters were male. So now I'm looking at all 500 of them. I'm doing 70% of the 500. So again, I know that 10% is 50. Multiply that 7 times. So 7 times 50, well 7 times 5 is 35 with a 0 on the end. I got 350. Is that what y'all got? And then I'm going to subtract 350 minus 160. Well, 150, 250, 350. It's not quite 200. So I say it's 190. And now I'm just doing some subtraction. So 300 minus 190 gives me, well, 190, 290. So a little over 100. A little over 100, I said, and then I wrote a 2. Let's see if that makes sense. Yep. Now I'm going to add 150. I ran out of room, but on your paper you can show me all your work. This is going to be step 1. In fact, you've already done step 1 of tonight's homework because you went through and made all the two-way tables. There might be one or two that you're going to have to make two-way tables for in the homework, but most of them you've already done the two-way table for. Now from that, we're going to find the probability. So here we have the probability we're looking for. And the probability, it asks me if we know the voter is from Virginia. So I know that the person's from Virginia. So I'm only looking at the people that are from Virginia. That's it. I'm only looking at those ones from Virginia. I'm not looking at everybody. I'm only looking at the ones from Virginia. So they're the ones from Virginia. What's the probability the voter is male? So I'm only looking at these guys. That's my total. Remember, with probability, I put my total on the bottom. So I'm going to have that 300 on the bottom. Then on top, I want the ones that are male. Well, I'm only looking at these ones from Virginia. So the ones that are male are these 190. Oh yeah, I'm going to show you the ultrasound. That's why this lesson is really my favorite, because I get to play with baby pictures. And then you get to watch this video. Tomorrow you're going to watch a video, and it's my favorite. This is just my favorite lecture. So this is 19 out of 30. And I think tonight I have you turn those into percentages, or at least give me an approximation. Well, we could have done an approximation of this. Just divide it by 3 to get it down to 100. So if I divide 190 by 3, I get a little more than 60. So it's about 60%. Is that right? About 60%. Yeah, 63. Jasmine says 63.33%. So about 60%. You can tell you divide that by 3, you divide the top by 3, so about 60%. How are you? Going into sonography. Get to look at images such as this over and over again. I'm going to show you all about it. Now, what were we finding? Well, I'm going to show you this notation. I think we looked at it back at the beginning when we talked about conditional notation, but we're going to look at it some more today. What we were doing is we were looking for the probability of males given we knew that they were from Virginia. I think that's the initials for Virginia, VA. So we were only looking at the people from Virginia, and we were looking at the males from Virginia. So we had this condition. All right, so this is basically what we're doing today. Look, y'all did it. We can do this. Nothing to it. So let me explain what Bayes Theorem is. And I'll tell you a little bit about the picture. And we'll talk about some testing. And this is my favorite lecture because it's just so relevant in your everyday lives, and especially for those of you going into medicine. It's just too relevant. It's too much of what you need to know. So let me explain first about Bayes' theorem. So this Bayesian thinking, the idea of Bayesian thinking, all it is just a simple idea that you have some preconceived notion. You think you know something. And then you get new information. New information is presented to you. And once you get that new information, it changes your thinking. That's all Bayesian thinking is. So I'm going to write that down kind of in words. So Bayesian thinking just says that, it just basically says that we have some initial belief. belief. Belief, belief, belief. I before E except after C, so it must be IE. Like that? We have some initial belief, something that we believe, and then we're updated with new knowledge. New information. And then it updates our belief. So Bayesian thinking says that we have some initial belief, and how about instead of updated, we say we're presented with new objective information, and we get a new or an updated belief. Now that happens all the time in life. You know, that's just a constant thing. You walked into your math class and you had this belief that math was hard and awful and you hated math. And then after being in this class, you're like, I love math so much, I think I'm going to take another math class. So you were presented new information and now you have a whole new belief about math, right? That's how that worked, right? Or, you know, a lot of times what happens to us when we get into college is we're like, I'm going to be an engineer. And then you take a class or two and you're like, I hate this. I don't like this anymore. I'm not going to be an engineer. So those are the types of things, you know, that happen just every day to us. We see something, we believe one way, we're presented new information, and then our idea changes. So that's all Bayesian thinking is. Then based upon that, we have this whole formula for probability. But all that is, this probability formula, is just that conditional probability. So like for instance, over here, if I asked you what's the percent, you know, let's just look at all those voters, what's the probability I get a male? Well, the probability I got a male was, whatever that was, 70%. So 70% was the probability that I got a male. But then once I knew they were a Virginia voter, once I knew they were for Virginia, the probability changed. The probability they were male was no longer 70%. Since I knew they were for Virginia, I was only looking at the ones from Virginia. So then it was a 63% chance that they were from Virginia. That probability changed once I had new information. So that's really all Bayes' theorem says. So I'm going to give you now the actual formula. So here's Bayes' formula, or Bayes' theorem. Here's the formula that goes along with it. It says, when I have the probability of some event given I know another thing. In other words, they're male and I know they're from Virginia. It's just that conditional probability. Then the way we find that is we find the probability of that event A, and we multiply that times the probability of event B given A, all over the probability of B. Matches my shirt, I think. Now, that's a big fancy formula that we're not ever going to use, because instead of doing it with the formula, what we're going to do is we're just going to look at our two-way tables. For me, making the two-way table is just the easiest way to go about this. Mr. Simpson has a video on Bayes' theorem where he makes a tree to help determine the Bayes' theorem. It's on my playlist. I added it to the playlist. If you want to look at that method for doing it, it's just another method that people use to figure out Bayes' theorem. So I like the two-way table. He likes the tree. Pick which one you like. Well, you've already made two-way tables, so if I were you, I'd use the two-way tables. But if you like the tree, or if you want to challenge yourself, whatever. So that's all this is a conditional probability, and then we're going to use it. So in this case, how did we use it? Well, the probability that they were male, was 70%. The probability they were male was 70%. We multiplied that times the probability that they were from Virginia and male. So in other words, we had to do the Virginia and the male. And that's what we put on top. Then on the bottom, we put the probability that they were from Virginia. The probability they were from Virginia. Notice that to get this probability, we actually had to add two things together. And if we were using it, we would have to do that as well. Yeah, that's right now what's happening. With coronavirus, this is being updated on a daily basis. We're finding out more about this virus. And so our scientists are using this Bayesian thinking on a daily basis as they gather more information and more data. Then they're like, oh, at first we thought that you couldn't just transmit it through breathing. And now it turns out that we're finding out more and more about it. So we're learning all kinds of stuff about it, and it's because our changing is thinking, because we're presenting new evidence constantly. So how does that relate to my picture of my sonogram? So I told y'all yesterday that the first time I went in for a mammogram, and really every time since then, the first time I went in for a mammogram, I got back a report that said that I was positive, that the mammogram showed positive things. And so I got that report and I didn't panic. And the reason I didn't panic is because I teach this lesson, this lecture exactly, where I show the probability. And we're going to look today to see what the probability was that I had breast cancer once I got that result back. And so what do they do when they say that they're positive? Hey Lucas, how's it going? What do they do once they say I'm positive? You know, do they immediately start giving me chemo? What do they do at that point? And then also another example of this in my family, I'm sure you've got lots of examples of this too, is, I don't know if you can see little Charlotte Lucille, but this is Charlotte Lucille. This is her very first sonogram. And she's so cute. She looks just like me, doesn't she? She's so cute. So when they go in and you do a sonogram, I got to be there for her first sonogram. I was there for it. And when you go in, we're not, as the mother and the aunt, I'm not paying attention to them doing things with it. Instead, what I'm doing is I'm just looking and going, oh, she's so cute. Listen to the heartbeat. Oh. But it turns out that with the sonogram, they're actually measuring things. They're measuring the length of the bones. They're measuring all kinds of stuff. And one of the things they're measuring is right in here. This little area right in here is called the nuclear fold. And that translucency there, that amount of liquid in there, they measure it. And if it's too thick, then that's a diagnostic test for certain chromosomal disorders, such as Down syndrome. So we had this sonogram done, and we actually didn't leave the office. And the doctor came in and said, hey, the baby is at risk for Down syndrome. This test, this measurement is thick, and so that puts the baby at risk for Down syndrome. Okay, so again, my sister didn't panic. She's a scientist. She too knows about Bayes Theorem. So when they told her that, she knew that what the probabilities and how probabilities work. So she didn't panic on that. Now, we had two different things that happened, because with my breast cancer, what they do is when you get this positive result back, they do further testing. And with the mammogram, that further testing is just an ultrasound. So they schedule up an ultrasound. It's not invasive. It can't hurt you to go in for an ultrasound. You can't be injured by it. So for me, it takes a little time out of my day to go in and do an ultrasound, but it's just an additional test to let you know, do you still see something or not? For my sister, the additional test is something called an amniocentesis. And I don't know if y'all are aware of amniocentesis or not, but those are invasive tests. In fact, they can cause miscarriages. They actually take the needle and go into the embryonic fluid and pull it out so that they can look at the actual DNA of the child. And so that one is more, there's some risk to it. That if you do that, you can end up losing the baby. So in my case, when I'm looking into the breast cancer, I'm like, sure, let's go ahead and do the ultrasound. Let's just check to see if I have it or not. Because if I have it, then we need to treat it. And if I don't, then I can quit worrying about it. In my sister's case, she's trying to weigh the risks, and she's like, I'm not willing to make those risks for the baby. So we had two different kind of options there. And I went ahead and went back in for the test, and she didn't. Now let's look and see, at least in my case, what was the probability that I actually had breast cancer. So, well, how much did I need to be worrying? So here's the idea of Bayes. These are the two-way tables we made yesterday. Yesterday we made 3 two-way tables, and the bottom one was the chance that I had breast cancer. So when I walked into the doctor's office, the women my age, it was a 1% chance, 1% probability when I walked into that to have my mammogram done that I had breast cancer. And we're going to see how does that change after I get back a positive test. But we'll do that one last. We're going to move back up here and talk about these two first, and then we'll talk about the mammogram. All right, so let's move to these two. And let me ask you some probability problems on it. So remember the one with the criminal justice here, or the crime scene, where the person identifies, they have a 75% chance that they correctly identify the race. So if you're one that's in criminal justice, that's another degree plan, that if you're going into criminal justice, you take statistics also. So not everybody out there is a nurse. Some of you are going into criminal justice. And here's an example of where Bayes Theorem comes up in criminal justice. There's a 75% chance that the person who's identifying the suspect gets the race correct. And we know that from the population, 84% of that particular population is white and 16% of the population is black. And I want to know, what's the probability that a perpetrator is black if the witness says they're black? So, we know that they have a 75% chance of being correct, but does that probability remain 75%? What's the probability then that if the witness says they're black, that the perpetrator is actually black? Well, so what we're going to do is we're going to look to see, what do we know? We're given something here. And because we're given something, it's going to change our probability. In other words, we have a new information coming in. And as you read the questions tonight, the hard part of this is figuring out what you know and what you're trying to find the probability of. So just reading the problem and getting your mind wrapped around it is the hardest part. I think that's always our hardest part, is just reading it and figuring out what it's asking. So here, what's the probability that the perpetrator is black if the witness says they are black? So we're not looking at the entire population anymore. We're only looking at part of them. Which part of them are we looking at? Can you figure that out from this question? We are definitely going to be looking eventually at that black column because we want to know what is the probability that the perpetrator is black. So this is the question we're asking, like what is that probability? That's who we're going to be looking at. But what is it that we're given? We know we're given that this witness says they are black. That's what we know. We know that the person came in, they identify, they say, well, the race of the person was black. You know, they were male, they were 34, and they were black. So I know that they said they were black. So which one of those numbers am I looking at? Well, I'm looking at the ones that were identified as black. And that was 3,300 of them. So 3,300 of them were identified as black. That's my denominator. The 3,300 is the denominator. Then I want to know from that what's the probability that they actually are black. So which number am I going to use for my numerator? Good. I'm going to use these that are identified black and are actually black. That's going to be my numerator. So notationally, here's what we're doing. We're finding the probability that they are black given that the person identified them as black. And my numerator is that 3,300, and my numerator then is 1,200. So yesterday, y'all didn't show work as you turned stuff in. I turned it back and said, show work. So you got to show me what you put in the calculator. Pretend you didn't use a calculator. Show me what you would have done. Today it's a little trickier to show work, because what are you going to be doing? Well, you're going to be looking at those two-way tables that you made. But notice, I just showed work. This was my denominator and that was my numerator. I just circled on there where the numbers were coming from. Now I'm going to reduce it. So, you know, if I want it to be about a percentage, well, I would divide the top and the bottom by 33. Or just to simplify it as a fraction, there it's 12 over 33. You could also say to get to 100, I'm going to multiply by about 3. So this is about 36. So about 36% of the time, when they identify them as black, they're actually black. Man, that's pretty awful, isn't it? So based upon these numbers, based upon these percentages, that it's a 75% chance that they correctly identify it, and that the population looks like that, when they say the person is black, it's only 36% of the time that they actually are black. Man, you would think that the probability would be higher, because it was a 75% chance that it was correct. And yet, it's only 36% of the time that when they identify them as black, they actually are black. So your thinking gets adjusted. You're thinking, well, 3/4 of the time they're getting this correct. And yet, when you start looking at the numbers and the probability, you realize that the probability is a lot lower, that when they say they're black, they actually are. Crazy, right? How's that for updating your belief system? All right. That's why you can't just go with the witness and believe everything what the witness is. Instead, you got to go find some other evidence out there to verify it. It does change what you were thinking. That's exactly the idea there of Bayesian thinking. All right, so that's how that works, like in the criminal justice system. And then to our medical testing, because we see this constantly within our medical system. That here we have a 1 in 1,600 chance of having whatever disease it is. So when I walk in the doctor's office, it's a 1 out of 1,600 chance that I actually have it. And in this case, I walk out with a, let's see, what is the probability the person doesn't have the disease given the test is negative? So in this case, what do I know? We walk out of there, perfect, Bo, we walk out of there with a negative test. So I now have a negative test. I know I'm negative. And you're thinking from that, the negative test, remember, is that specificity. So 95% of the time, if I don't have the disease, 95% of the time when I don't have the disease, the test shows that. So here, I want to know, once I have a negative test, what's the probability that I don't have the disease? Now, you might be thinking that it's 95% because the specificity was 95. But let's see if it actually is. Once I have a negative test, what is the percent chance that I don't have the disease? And y'all have totally got this. Because this is you're right, that's your denominator. And the don't have and the negative then is your numerator. So in notation, the probability I don't have it, given I had a negative test, well, the negative tests are my denominator, and my numerator are the ones who don't have it and got a negative test. Let's do some reduction there. Just tell me what is that percent? I mean, those look really close to one another. This number is almost the same as that number. If I had to tell you what the percent is, without a calculator, I would say this is like 99%. I would say that's like 99% approximately. Almost everybody who walks out with a negative test, because those two numbers are so close. I mean, we're just 10 away, and the numbers are so big that this is almost the same. So it's almost 100% of them. Jasmine says it's 99.99. So almost everybody who walks out with a negative test does not have the disease. And that's what this, you think it would be 95%, but it turns out that if you get a negative, most likely you do not have the disease. It's very, very rare then that you actually do have the disease. So if I have a 95% specificity, it's actually really, really close that I'm not going to have it, especially with this prevalence. It might change if the prevalence were different. What about if I changed the wording of this? What about if I said, what's the probability the person doesn't have the disease given the test is, let's just make this last word positive. What if I say instead of negative, I make this last word positive? How does that change my question? Good. My denominator is just going to change to the positive test. And you might instinctively think, well, if the sensitivity is 90%, you might be thinking, well, then 10% of the time you would walk out with a negative. That's kind of what you might be thinking. But let's see in actuality what happens. So I'm going to make this a positive. It still don't have, and you're right, it changes it from here, and then it's got to be the ones that are positive and don't have it. So it changes, both my denominator and my numerator become that part. You're exactly right. So now let's look at the probability. So that I have 8085, and on top I've got 7995. So I walked out with a positive test. I walk out with a positive test. What's the probability I don't have this disease? Well, again, those are pretty close to one another. It's going to be pretty high that I don't have the disease. So, divide that by like 80. Oh, man, it's going to be really close, like 90, 97, 98%. So y'all tell me, what is that percent now of people who got a positive test but don't have it? 98.89%. Look how high that is. So most of the people that walked out with that positive test did not have the disease. Think about that for a minute. You walked out with a positive test, and yet you didn't have the disease. Thank you, Mr. Simpson. So it reduced to 533 over 539. If I divide it by 5, maybe something else goes in there, but at least 5. Almost, it's 99%. I mean, it's almost everybody who walked out with a positive test did not actually have the disease. So it just is, it updates your belief. It updates your understanding once you know this more information about it. So for me, when I went in for breast cancer, I know the prevalence is about 1 out of 100 women my age have breast cancer. So what is the chance? Well, when I walk into the doctor's office, that means that my probability is 1 out of 100. Then I get a positive test back. So maybe I start to panic because I get this positive test. But let's see what is the probability that I actually had the disease. So in my case, what's my denominator going to be? My mammogram's positive. What's the probability I had breast cancer? So what's my denominator going to be there? Which one of those am I going to be looking at? Yeah, exactly, those positive tests. So I'm only looking at the positive tests, which the positive test, my denominator then is going to be the 1,089. You're exactly right. I'm one of those 1,089 people that got a positive test. So then I start to get anxious, and I'm having to worry, and I call my doctor and I say, now what? And I start making all these am I going to be able to work next year? Maybe I should quit my job. Should I, start getting my affairs in order, get my will taken care of? Who's going to take care of my kids? All these things that you start to worry about when you get that positive test. And the question is, what's the probability that I had breast cancer? So what's going to be my numerator? And by the way, the sensitivity of it is 99%. That means 99% of the time, if you have breast cancer, it's going to catch it. 99% of the time, if you go in for a mammogram and you have breast cancer, the mammogram is going to give you a positive test. So you're thinking with that high of a level, you're thinking that it's a 99% chance I had this thing. And yet, let's look and see. So my denominator is the ones that's positive. I'm one of those positive people. I would have to be one of these 99 in order to have breast cancer. So here's the notation. Let me use the black so you can maybe see it. The notation is the probability that I have breast cancer given that I got a positive test. And my denominator is 1089. And my numerator is 99. Am I one of those 99 out of the 1,089 that have breast cancer? Well, I need to divide by 10 to get down to 100. So divide by 10 and you get about 10%. About 10%. Y'all agree with that? That it's about 10%? So I started with this 1 out of 100 chance. Then that's scary enough, just thinking that it's 1 out of every 100. But, I'm not too worried about it. Then I get this positive test back, and I know that 99% of the time it's going to catch it if I do have it. But instead, so he says it's a little bit less, it's like 9%. Good, Jasmine, yeah. Jasmine says it's 9%. So it's just 9% of the time, if you get that positive test, you actually have it. And yet these tests are really good. Look how good it was. It was a 99% sensitivity. In other words, 99% of the time that you have breast cancer, it's going to catch it. And 90% of the time, if you don't have it, it's going to say you don't have it. And yet, it's only when I got that positive result back, it was only a 9% chance that I actually had breast cancer. That's the reason when I got that positive back in the mail, I didn't panic. I thought to myself, well, the probability is still low that I actually have breast cancer. I need to have another test done to find out if I do or don't. And that other test that I needed to have done was not invasive. It wasn't going to hurt me in any way. The only thing it was going to do was cause me some time and maybe a little money to go in and have that test done. So I had the test done. I did not have breast cancer. Every single time I go in for a mammogram, I get back a positive result, and I have to go in and have this ultrasound done. Now, I go in and do the ultrasound every time because it's easy and it's cheap and it doesn't cost me that much. But if it were like a major test I was having done, maybe I wouldn't have that second test because I know this probability is so low. But here's what's happened. The guidelines for when you have mammograms has actually changed because of this. Many women were getting back a positive when they didn't actually have breast cancer, and it was causing this anxiety. And things were happening with the women because they got back this positive result. All of a sudden, that's a whole nother medical issue in itself, that you got this anxiety, You're making life choices thinking that you have breast cancer when you don't actually. So they changed the guidelines on when women are supposed to have mammograms. It used to be at 40 that you were supposed to go in for your first mammogram, and I think now the guidelines are at 50. You go in for your first mammogram. Unless someone in your family has breast cancer, or you're at risk some way. So now I'm at risk because I keep showing this positive every time. So now I'm at risk and I have to go in over and over and over again. And exactly like Mr. Simpson said, too many false positives, too many of these guys, too many false positives. I was one of those 990. Too many of those false positives causes anxiety, it costs money, it's a drain on the medical system. So they actually changed it so that you're not going in every year for a mammogram, and you have to be older to start unless you already have a risk factor. So just, things actually are changed based upon statistics. And I did not have cancer. No cancer for me. No cancer for me. Now, normally, at this time of the class, we would figure out the probability that my sister had Down syndrome. And it would be a big reveal to find out if she has Down syndrome or not. But y'all already know because you did a pre-assessment on it. So it's kind of I don't get to give the reveal here. And part of your assessment is you're going to figure out my sister's probability that her baby had Down syndrome when she got back that result. You gave me what you thought that probability was. You already turned that in. That was your pre-assessment. You told me what you thought her probability was. But now that you know a little bit about things, she is so adorable. Wait till you get to watch the video. She's so cute. So now I want you to go back and see if your thinking has changed now that you know a little something about Bayes' theorem. After you've been given this new updated belief. And that's going to be your post assignment, is to figure out that probability and tell me how your thinking has changed. Then I have a video for you to watch about Charlotte. And then afterwards you can also tell me how you're changing, if your thinking has changed any at all about Down syndrome as well. All right, so that's how Bayes' theorem works. Once you have new information, your thinking changes and your beliefs are updated. Hopefully you now have a little bit of new learning and updated beliefs, and the next time you get a positive test back, you won't freak out. You'll go to your doctor and say, okay, what test do I need to have done next? Math made simple. That's Simpson Math. Thanks for watching.